A couple of updates. We had midterm on Monday. How many of you thought that the midterm was easy? Good. Hard? A few. Okay. So that's fair. I think we had over 300 people writing the midterm. Please don't discuss the midterm because there are some students who are at the conferences right now. And we're going to have a markup. So there's a second midterm, which is going to be different. But still, hopefully we'll resolve that within 1 week. Because we need to make sure there's like 10 people or so that will need to write a separate midterm. OK? Couple of things. I think there's a few people were asking, curving and that kind of stuff. We'll have to look at the grades. Obviously, at some point, we will do curving, depending on what the averages are for the midterm. But at the same time, if you are, let me put it this way: the goal of this course is not to flunk people. I think that in this course, you will have a lot of homework, right? And your project, which will take some time. But at the same time, if you're doing well on your homeworks, you're doing well on your midterms and such, you're going to be fine. So I wouldn't worry too much about you not finishing some problems on the midterm or anything like that. This is a graduate level course. This is not an undergraduate level course, right? And for the graduate level course, the goal is for you to learn as much as you can and adapt and do your homeworks. And I know that sometimes homeworks can be difficult, especially for those who've never done this before. And your second homework is not as bad, but once you start training these RBM style models and such, it will be a little bit challenging, right? Because the first time you do it, it is challenging. So the goal is for you to learn as much as you can, and I don't think you should worry that much about the grade being here, this or that. And the average, I think the average on the first homework was like 93, is that right? Something like that. So that's good. You guys did a good job on your first homework. Let's continue doing the second homework. And hopefully the midterms will release the midterms back to you maybe in a week or so once we finish everybody else taking the midterm. So it's fair for everyone. Work on your second homework assignment. Also, your projects, one-page project proposals are going to be due in 2 weeks, right? I think it's going to be on Monday when your second homework assignment is due. So you'll have both your second homework assignment and one-page project proposal. For the project proposal, again, it's a one-pager. Just outline what is it that you're going to be doing, what kind of data sets you're going to be using, and what's the approach that you're going to be taking. This doesn't mean that you have to commit to using exactly those approaches and exactly that data set. You can change, the things can change as you progress, but at the same time it gets you thinking about who you're going to be working with, what the overall project that you're trying to do. So try working on that. And that also gives TAs the idea of who's working on what project, so we can divide projects among TAs, and so if you have any questions, you can talk to TAs about your specific project. You can talk to me, but you can also talk to TAs. Okay? Any questions? All right, so, and I think that a couple of weeks down the road, once we have the midterm, I'll show you the solutions for the midterm. Once you look at the solutions, in hindsight, you'll realize how easy the whole thing is. So everything looks trivial in hindsight, right? So, okay, so today we're going to talk about autoencoders. That's the last piece that you will need to for your homework. And autoencoder is actually one of probably most widely used methods, even more widely used than restricted Boltzmann machines, because they have a proper objective function that you can train. So, and again, I'm using some of the lecture notes coming from Hugo. Autoencoders. We've looked at the autoencoders just a little bit, right? You can think of them as, in this case, it's just a one-layer neural network, but where you have an encoder, you have some input, it goes through some sigmoid nonlinearity, and then you have a decoder. And the decoder is trying to reconstruct back the original input. So for example, the output here would be sigmoid output if you're working with binary data. So in your homework, you're working with digits, and the output is just going to be the sigmoid because the digits are binary. So, and this is for binary units. And in general, the autoencoder, you can think of it as there is encoder, takes the input, encodes it into some feature representation, and then there is a decoder. Right? The decoder is just basically taking feature representations back into reconstructing or representing inputs. So this framework's been around for a long time. I think autoencoder has been introduced 20, 30 years ago. But these blocks, what goes inside encoder and what goes inside decoder matter a lot. And different algorithms can be derived. In fact, a lot of different algorithms. People talk about here's an encoding function, here's a decoder, and such. So typically the encoder is feed-forward, bottom-up, much like in neural networks. Given the input, you're trying to infer some hidden states. And the decoder is generative or feedback, right? And sometimes so top-down. People call different names. It's also called sometimes generative, just like in restricted Bose machines, because you can generate back the original input, right? You can reconstruct back the original input. And what goes inside encoder, decoder matters a lot. So binary autoencoders, given the input, let's say you have an image, which could be a real-valued image, not necessarily binary. You can encode it into the binary features by just using sigmoid nonlinearities, and then you're going back and you reconstruct back the original input. Okay? The encoder, just basically a simple sigmoid function, and the decoder could be a linear function. Okay? So whenever you work with the data that's real-valued, like real-valued images or whatever data you're working with, the encoder could be sigmoid, some nonlinearity, and the decoder could be just a linear function. We'll see it some extensions of this model. And one of the things that you need to do is you need to introduce some additional constraints when you're looking at this particular model, right? One constraint is that you somehow need to be able to learn to avoid learning identity function. Right? Because I can always do the following. If I can make this be identity function and this be identity function, then I will have perfect reconstruction. Right? So I take an image, I call my features pixels, I reconstruct back the original limits, it's perfect. So obviously you need to enforce some constraints. Right? This particular problem doesn't occur in Boltzmann machines, so undirected graphical models, right? Like in restricted Boltzmann machines. The reason why it doesn't occur there is because you're not trying to do reconstruction. You're trying to model the distribution over the observed data. So in RBMs, interestingly enough, you can have a very high dimensional hidden state, and it's not just going to learn to copy the image back and forth. And also, it relates to restricted Boltzmann machine, as you can see. The objective functions are different. And also, the encoder and decoder filters can be different, right? So the encoder can have its own parameters. Decoder can have its own parameters. Now, let's look at some loss functions. For binary inputs, your loss function would be cross-entropy error loss, right? What does it look like? Well, it would be just the reconstruction loss or cross-entropy error loss, right? Because what happens is that given the original input, you go through the hidden state, and then you're trying to predict what the inputs, what the reconstruction should be. Those are the probabilities coming from the sigmoids, right? And you also have the correct target. You know what the right pixel values should be, right? So it's almost like you're trying to predict the value of every single pixel. And it's a binary pixel, so it's kind of like solving, in your case, it's going to be solving 784 binary classification problems, right? Because for every pixel, you have to predict, is it on, is it off? For the next pixel, you're predicting, is it on, is it off, right? And you can use cross-entropy loss function or reconstruction, cross-entropy reconstruction loss. If you're looking at real-valued images or real-valued input, then typically the reconstruction loss is just a squared error loss, right? So it's just going to have your standard squared error loss. And again, depending on the problem that you're trying to solve, you will have different loss functions. So just like for any model, even for autoencoders, you have to define what the loss function is. What is it that you're trying to reconstruct, right? So depending on the types of input, you will have the corresponding loss functions. The two most commonly used one is the squared error loss, because your input has some real valued input, or cross-entropy error loss. Okay, loss functions. Oh. Let me just put this thing, otherwise it looks funny. It didn't copy the equation. So for both cases, the gradient of the loss function for both cross entropy and for square error loss, you have this form, right? It's the prediction minus the target, right? The prediction is the predicted reconstructed input. The x is the actual input, right? So how far are you off? I think on your midterm, you had to derive, the gradient with respect to the cross entropy error loss if you got the question correct or not, right? So with a little bit of math, you should have seen that, it's going to come to that, right? It's just a difference between prediction and the target. And then the parameters can be obtained just basically doing backpropagation, just like in standard neural network. When you use tied weights, when the encoder and decoder uses the same set of weights, for a lot of problems, people use the exact same set of weights, then you have to ensure that, when you take the derivatives, you have to ensure that both weights are the same, right? Typically, you take derivative with respect to the decoder weights and then the encoder weights, and then you average them. That's just deriving it from the loss. So the gradients are just going to be the sum of the two gradients, or the average of the two gradients. Okay, so how do you adapt the autoencoder to a new type of input? Well, the first thing to do would be to choose a distribution of P of x given the parameters, where mu is the parameters of that distribution, right? So for example, this is something, we'll look at some of these examples. But you have to figure out what's the distribution of the input that you're trying to model, right? If it's a real valued input, it's a Gaussian. If it's a binary input, it's a Bernoulli model, right? In some cases, if you believe that your output only is positive, you might want to use a gamma function, right? Or if you believe it has Poisson type of distribution, like a count distribution, then maybe it should be a Poisson model. You choose the relationship between mu and the hidden layer, and then your loss function, your reconstruction loss, is just going to be the log probability, the negative of the log probability. Okay? So let's look at the example. In the case of squared distances, right, how do we actually do it? Well, we choose a Gaussian distribution with mean mu and identity covariance. So we're basically saying the way that I'm modeling my data, P of x, given some parameters, mean, is just going to be given by a Gaussian distribution with some fixed variance, right? And mu here is going to be the states of the hidden layer, right? So given the states of the hidden layer, you're basically saying how am I reconstructing, what's my distribution over the outputs? If it's a Gaussian distribution, then you can formulate that this is my distribution, the Gaussian distribution, and then if I actually take the log of it and start optimizing for it, then you get the squared error loss, right? Exact same thing happens for the Bernoulli model or working with binary data. You can write down this probability as a Bernoulli model. If you take the gradient of it, you get cross-entropy error loss. There's been some work on modeling word count vectors using Poisson model, where this thing will count, how many times you observe the word one and how many times you observe the second word and so forth. So this model can be a Poisson model. And when you derive the reconstruction again, it's the loss that you are deriving. Let me show you just one example. This is Emny's data set. You've seen that. And if you actually learn features based on autoencoders, just looking at the reconstructions, versus restricted Boltzmann machine. I think this is RBM with one-step contrastive divergence. This is what you're going to be doing on your homework assignment. This is trained on 60,000 images. You're only going to be training, I think, on 3,000 images. It's a much smaller data set. So you will probably you're not going to see as crisp filters as you're seeing here, but roughly something similar to that. You can see that RBMs in many cases actually picks up, the features that it picks up are much sharper and better than just the standard autoencoder. You can see there's a lot of kind of just not a lot of structure that you see when you're training an autoencoder model, right? So you need to introduce a little bit more constraints for that model. Any guesses why such a difference between the two? If you think about it, what's the autoencoder? It just encodes, decodes, and you look at the L2 distance, or you look at the cross-entropy error for reconstructions. RBMs, you just go up, down, up, and you're looking at correlations between X's and H's. So why is one doing much worse than the other one? Can you guess? Because these features are much better than autoencoder features. Let me give you a hint. When you're doing restricted Boltzmann machines, given an input, you infer the states of the hidden variables. What happens to the states of the hidden variables? You sample them, right? Once you sample them, they become binary, right? So now the model has to learn to communicate through this binary vector the reconstruction. So it's a stochastic process. And the only way for a model to do that, it's almost like there is a bottleneck, right? Given the input, I only have a few hidden states that are binary, a few hidden states that take value 1, the rest is 0. So the only way for me to communicate information from X to the reconstruction is by learning features that, you know, a few instances of those features you have to be able to reconstruct. It's almost like you're injecting stochasticity and you're injecting bottleneck. In an autoencoder, it's real valued. I go up, everything is real valued. I go down, I do reconstruction. So there are no constraints on the autoencoder. In fact, autoencoder will reconstruct data much better than an RBM. Right? But that comes back to the problem that if I actually make my hidden state to be an identity, then the autoencoder doesn't need to learn anything. Right? So that's why when you think about autoencoders generally, in this case, I'll show you some examples where we really need to think about enforcing additional constraints, because otherwise the model will just learn to overfit. Okay, now, optimality of the linear autoencoders. There is actually a very nice connection that if the hidden and output layers are linear, then the k hidden units are going to span the same space as the first k principal components of the PCA. So in fact, if you have a linear encoder and decoder, right, then you're essentially going to be recovering PCA. Right? It's going to span the exact same subspace as PCA. So that's kind of neat, right? Because it's basically saying that if you just have linear encoder decoder, you're effectively doing PCA. And as you know, PCA is very commonly used method, right? It's a dimensionality reduction, that's your friend. Anytime you say high dimensional data, you want to reduce it dimensions and maybe look at two-dimensional representation of the data. PCA is the first thing to do because there's an exact solution to that. There is a solution, right? You just construct covariance matrix, take eigenvalues, and look at the corresponding eigenvectors. With nonlinear hidden units, you have a nonlinear generalization of PCA, right? So nonlinear PCA can be much more effective at discovering nonlinear representation of the data compared to linear PCA. And I'm going to show you some examples of that. So optimality of the linear encoder, just to maybe just basically look at that. This is primarily for your own background. It's just a little bit of linear algebra. Let's say we have A be any matrix with singular value decomposition. So sigma here is just going to be diagonal matrix. V and U are orthonormal matrices. These are, columns and row are orthonormal vectors, right? This is a standard singular value decomposition. And if you let U, sigma, and V here be the decomposition where we keep the k largest singular values, then this holds, right? This is just basically saying, I'm not going to spend a lot of time, but this is basically saying that, if you want to look for the optimal matrix such that it's closest to your matrix A in Frobenius norm, but the rank of matrix B is k, then the optimal matrix is going to have this form, right? So which is essentially saying, if you're trying to look at the squared error loss between A and B, in this case it's a Frobenius norm, right? It's just sum of the squares, and you're looking for the matrix B with rank k, then B has to have this solution, right? Just corresponding to the top eigenvectors. And if you want to look at the proof of this particular claim here, that's your proof. Okay? So I'm not going to go through the proof. Feel free to go through the proof yourself. It's pretty straightforward, just a little bit of linear algebra. And it's good to go through that proof because it really does show that, this is how singular value decomposition works. And it also shows that, for the optimal pair of encoder-decoder, it's going to have this particular form. So if I have linear encoder and linear decoder, and I look at the sum of the squared difference error, and I look for the autoencoder with a linear autoencoder and linear decoder, then the optimal set of weights going to have this property. They're just coming out from the singular value decomposition, right? And this optimality here means the lowest training reconstruction error, okay? So you basically just do PCA, you plug it in, and you have the optimal reconstruction error, right? In a linear encoder-decoder model, which is kind of neat, right? Because it makes the connection between autoencoders and PCA. Because everything is linear, then we have an optimal solution. Once you start introducing nonlinearities, you no longer have the optimal solution. Sometimes people actually use PCA to initialize autoencoders. Might help. Sometimes it helps, sometimes it doesn't. But you can. And if the inputs are normalized, then you just have to make sure that everything is zero mean, obviously, just like in PCA. Then the encoder would correspond to the principal component analysis, and singular values is going to be eigenvalues vectors of the covariance matrix. So that's your standard PCA. You can look at deep learning book, you can look at Bishop book. There is a little bit more of that, but again, it's just a standard linear algebra, okay, which you should be familiar with. I know that a lot of times people ask these questions when you go through job interviews and stuff like that. So. Know the singular, what is the singular value decomposition and stuff like that. Okay, now, there are a couple of ways we can think about autoencoders. In many cases, we can think of the hidden layer to be bottleneck layer, right? Or we have an undercomplete or smaller than the input layer. In many cases, we can think of these models as dimensionality reduction. Right? So now the model can't really learn identity because you say, I have some high dimensional input, I'm squeezing it through some small bottleneck, and I'm trying to reconstruct it. So you're really looking at the subspace, some representation of high dimensional data in the small dimensional subspace. Typically, one application is dimensionality reduction. So the hidden layer here compresses the input. And if you have perfect reconstruction error, that means that you've perfectly compressed your input, right? So we'll compress only for the training distribution, obviously. And so when you look at the hidden features, these representations H, they're going to be good features for the training distribution, but they might not be robust to other types of input, right? And that should be obvious, right? If I use my training set, and somehow at the test time I give you inputs that are coming from different distribution, obviously this will not work, just like any other machine learning algorithm. So that's something to be aware of, right? So it could be learning good features, but if I put this thing in as an input, guess what it's going to do at the output? Any guesses what would happen if I give this, like if I'm training on my MNIST digits and I give it a noise or something that looks like a noise? What do you think the output would look like? Guesses?
Some digit?
Yeah, it will look like some digit, or like some noisy version of the digit. It will try to fit it into, because if you're only training on digits and you give it something else, it will try to reconstruct back the original digit, right? Because that's what it's seen during the training time. It will try to put it onto the manifold of the digits and reconstruct. It's going to be noisy reconstruction, but nonetheless. So you have to be careful, training on this and then testing on something completely different. Overcomplete representation. Now, this is something that people looked and say, well, what if we have overcomplete representation? There is no compression here. Each hidden unit could copy different input component and just copy it, right? Obviously. So no guarantees that hidden units will extract meaningful structure, because I can just take part of my input, copy it, the X could be garbage, and then I just reconstruct it back. So if my optimization is right, I can hit zero training error by just learning the identity, right? So that's not very useful. And so for a long time, people were thinking about autoencoders as compression mechanism, just bottleneck. You have to pass it through the bottleneck. It's dimensionality reduction. Then there were a few papers that basically said, well, what if we do the following? The idea would be to learn representations that are robust to some noise, right? So now you're basically saying, well, I'm now going to be injecting some noise in my inputs. Think dropout, for example, or other kinds of noise. And this paper, there was a paper back in 2008 before the dropout paper. This was done by Vincent. And what you're doing is you're saying, well, what you want to do is you want to basically do dropouts on the input. So you shut down part of the input. Or you can add some Gaussian noise, right? Take an input, add some Gaussian noise, and so you're corrupting your input, but then your reconstruction, you want to be able to reconstruct the original clean digit, right? So I give you corruptions of the inputs, either by noise or by masking some of them, setting them to 0, but I want to be able to reconstruct back the original input. So here's the way you can think about it. There is some corruption distribution, P of x tilde given x, here. Whatever that corruption distribution could be, some noise process that creates the noisy version of x. But then from this noisy version of x, you want to be able to reconstruct the original x. Okay? It's a very simple technique, but it turns out that it works really well. I'm going to show you some examples. So the reconstruction x is computed from the corrupted input, right? And the loss function compares your output with a noiseless input. So you really want to be able to denoise the data. That's why it's called denoising autoencoders. Yes, question?
W star and W transpose are the encoding and decoding weights, and they're the same here?
Yeah, they're the same. This is just to show that in this particular work, these weights, these W's were the same in encoder and decoder. Sometimes you can make them be different. Sometimes you make them be the same. Obviously, if you make them be the same, you have twice as few parameters to fit. So it's done particularly for regularization purposes. Yes?
We need to put the W for different noise levels.
No, I mean, generally you fix some noise and you learn W. So you fix the noise process and then you learn the parameters.
But if my noise level increases, then does this network still work?
So if you're training with a particular noise and then at test time you introduce completely different noise, it might not work. Right? The idea here is to really find, can you learn some hidden representation, some features that are going to be more useful? And it turns out from the way that you think about this problem is that if I give you some input X and I corrupt it, I get off the manifold, right, of my data. And then the autoencoder, what it's trying to do is it's trying to bring it back to the manifold. So you're basically saying just around the manifold, if there's some corruption, some noise corruption, I want to be able to handle that. And generally, like for example, here's an image with some noise, right? Where some pixels are blanked off. And you want to be able to reconstruct the original input, so you're kind of bringing it back to the original manifold. And here's what happens with the features. Now, this is not a generative model in principle, right? It's not like I can generate these images. These are more like a denoising model. But what happens is that, if you add 25% corrupted input, so you block out 25, it's like a dropout of 25% on the input, then you start learning much better features compared to not doing that. And these features are sort of, you can see little edges, little detectors. If you actually do 50% corruption, then you start picking up more relevant features, right? So you're not just doing kind of noise, you actually start picking up little edges and little corners and stuff like that. And they've shown that this particular representation here is much better for doing classification. Like if you want to, based on these features, classify, is it a digit of a 2 or of 3? This is a much better representation, right? So that's a neat trick to know about. It's almost like doing dropout, but obviously you can corrupt your input with Gaussian noise or whatever noise you believe you should have whatever noise you'll have in real life. That's something up to the modelers to decide what kind of corruption you want to do. For squared error loss, if you train it on natural images, this is how the data looks like. I know it looks like random, but these I think these are like 10 by 10 patches that you take from real from natural images, and these are the filters that the model is learning. This is also based on denoising autoencoders, so it's learning some interesting structure based on images. And PCA in this case actually doesn't do a good job. This is what PCA does. So here's PCA solution, I think. Okay, now there is another class of autoencoders that it's good to know about, which also kind of has this interesting representation. So it's an alternative approach to avoiding uninteresting solutions, right? What you want to do is you want to add an explicit term in the loss that penalizes that solution. Okay, so let's look at what I mean by that. One thing that you'd like to do is you'd like to find representations, you'd like to find features that kind of look at the variations in the training data. And we'd like to be invariant to other kinds of variations. For example, for digits, they can be slightly rotated and so forth. But maybe you want to be, invariant to other variations like scale, for example. So here's the trick. It's called a contrastive autoencoder. It's actually pretty, it works very well in practice, so you should know about this. Imagine that you have some reconstruction loss, right? This is your standard reconstruction loss. And then you have this funny term. Let's look at this term. This is the Jacobian of the encoder. What's the Jacobian of the encoder? You take the derivatives of the hidden features with respect to the input. Okay? Now let's think about this. You take the derivatives of the hidden states with respect to the input, and what is it? And you're looking at the L2 norm of that. So this term would be happy, right, if the derivatives of the hidden state with respect to the input would be 0. What does that mean? That means that the hidden state would be completely independent of the input, right? So you basically want to say, I want my hidden state to have nothing to do with the input, right? That's what this term is trying to do, right? So it's basically saying that any changes on the input space will not change my hidden states, right? That's exactly what the Jacobian is trying to do. It's almost like trying to penalize the gradient and say the gradient should be 0. So any changes to the input will have no effect on the hidden state, which is kind of silly, right? But at the same time, you also have this reconstruction loss. So you're basically saying, I want to be able to reconstruct my data, right, as well as I can. At the same time, I want my hidden states not to be very sensitive to the input, right? And that's the penalty term, or that's the regularization term. So now you're kind of learning these representations that you're encoding and you're doing reconstruction. At the same time, they're much more insensitive to the small perturbations in the input. So if I take my 2 and I may change it a little bit, it's learning not to really change the hidden states and reconstructing back the original 2. Yes, the question?
I guess you might have answered it, but like how that is encoding, avoiding uninteresting solutions. Yeah,
so it's trying to avoid uninteresting solutions because it's basically saying make sure that directions in this hidden space that are responsible for actually modeling the digits, like if you think about the manifold, right? Whatever happens on the manifold is important. Any directions of this manifold shouldn't impact the hidden states. And so, for example, this is the contrastive term for the binary observations, right? So you take the derivative of your hidden states, which is the sigmoid, with respect to the input. And you're really trying to make sure that they are not very large. It also forces the model to say, well, small changes in x shouldn't result in big changes in h, right? You really want that term to be very small. Yes, question?
Following your explanation, then wouldn't that gradient should be constrained to the normal direction of the manifold to the gradient of the manifold?
Yes, but you want it to be small. So any direction that's orthogonal to the manifold that's not going to affect your loss is going to be small. You want it to be 0, actually. right? Because remember, this is what we're trying to minimize this thing, right? So that's exactly right. Any directions orthogonal to the manifold, you want to shrink them and say, I want them to be 0. I don't want to move in these directions. You only want to move along the manifold of where the real data is. So whatever changes in X you need to do to reconstruct back the original input, this loss will take care of. Any other directions in the H space, any sort of that don't really affect your loss, you want them to be 0. It also brings a little bit of robustness because it does say that the gradient should be 0, right? Which basically means changes in the input space shouldn't result in big changes in the hidden space. So it adds a little bit of regularization that way. So here the autoencoder attempts to preserve as much information as possible about the input, and encoder here throws away any other information, right? That's not relevant to the input. And this is exactly what happens. Imagine you have these digits on the manifold, right? The encoder doesn't need to be sensitive to this variation, right? If I move my data this way, right? So I want this variation not to be sensitive, right? So that's why I'm shutting it down. I only want my model to be sensitive across these variations. Right? And so the encoder must be sensitive to this variation to reconstruct well the original input, but it must be insensitive to anything that's orthogonal to that. The pros and cons. Advantages of denoising autoencoders, it's simpler to implement, right? It basically requires just a couple of lines of code to your original model, so people are using that. You no need to compute the Jacobian, but the contrastive, for the advantages of contrastive autoencoders, you can use second-order optimizers, like in principle you can use LBFGS to do the optimization, and it might be more stable in denoising autoencoder. So generally, if you look at the literature, there's been some papers looking at contrastive autoencoders, and they're a little bit more robust. And obviously, you can apply kind of similar types of ideas. There's been a few papers looking at the sensitivity of the hidden features with respect to the input and so forth by taking the gradients of the hidden states with respect to the input and kind of constraining that to be small. OK, now back to the autoencoders. You can encode, you can decode. This is feed-forward feedback connection. And again, there's been a lot of work, people trying to figure out what exactly should go into encoder and what exactly should go into decoder. Here's one particular model. It's called predictive sparse decomposition. What you have here, and when we look at the sparse coding models later in this class, we'll look at these models. But what these models are doing is they're basically saying, well, I have my encoder, and I have my decoder. They have different parameters, but I'm also going to put sparsity. I'm going to force my hidden states to be sparse. Okay? And sparsity really helps you to find, first of all, much better features. People have shown that. And you obviously control the capacity of the model. But now you have basically the following setting, right? You have an encoder. This one, just a simple sigmoid. You have binary features Z. So you're trying the encoder to say, well, I want this term to be small. At the same time, you have a decoder where from Z, you're trying to reconstruct back the original X. But you're also trying to put the L1 sparsity constraint here as well. Right? And so you're minimizing over D, W, and Z. You're trying to make this term as small as possible. And this L1 term here forces these Zs, these learned representations, to be sparse. So this is sometimes, this particular model, the model at the bottom here, is known as sparse coding model. Okay? And you can also do the following. You can stack these features. And people have been doing that. Depending on what problem you're trying to solve, you can build little sparse predictive decomposers layer by layer and so forth, and stick the classifier on top of it. So there's been a few papers in that space as well. Even though at this point, one question you might ask is, okay, why is this? What is this doing, right? Like, why stacking autoencoders is so interesting Is it optimizing a particular objective function? Is it doing something? Or are you just hacking things up, stacking things together? And so before 2006, people knew about autoencoders, but this idea seemed a little bit crazy because you're just hacking around. I can't write down an optimization or a loss function that will tell me, by doing this, you're doing some form of an optimization of any loss function. It's more like, stitch things together and look, it works, which is fine as well. But there was no reason for people to say, why would this make sense? This is kind of like a greedy layer-wise learning. But in principle, you can stack these things. You can throw away the decoder. You convert it into the feed-forward, the convolutional net, and voila, you have your deep neural net. Right? And now there is a question, top-down, there is bottom-up. People are talking about, well, we just do feed-forward. If you talk to neuroscientists, we'll say, well, the human brain does bottom-up. There is some feedback that's happening. We're not modeling that. Is there a more rigorous mathematical formulation for these models? And later on in the course, we're going to look through that as well. When we start looking at something a little bit more complex as variational bounds and such for analyzing these kinds of models. Just wanted to show you a couple of examples. Here's an example of building a deep autoencoder. Imagine that I give you these faces, and I do pre-training. In this case, you can use RBMs, so you can use denoising autoencoders. They work about the same. But here you train a whole bunch of these things, layer by layer. Right? So you first train your first layer RBM, you infer the hidden states, you train the second layer RBM on top of the first layer RBM, and so forth. And then you can unroll it, and then you can fine-tune it. Right? And this is a really deep autoencoder where you have an input, you pass it through many hidden states, you find the 30-dimensional bottleneck, and then you reconstruct back the original input. These are not convolutional models. These are just feed-forward, fully connected models. So you can see it kind of does the reconstruction of the face. Here's an interesting thing. So here you look at the top face. Top row shows the data. And these are test images. These are test faces that the model is not trained on. The second row shows reconstructions done by this deep autoencoder, again, with a bottleneck of 30 dimensions. So you're really trying to do the compression of, in this case, these are 28 by 28 images. So you're going from 784 dimensions to 30 dimensions, and you're trying to preserve as much information as possible, right? And the bottom shows the PCA solution. If you do PCA, 30-dimensional PCA. So you can see that the PCA kind of looks like, a lot of faces look like snowman faces, like this one, because it has to smooth things out. It can't really model anything sharp. These are reconstructions done by nonlinear extension of PCA, right? That's a deep autoencoder. It's interesting, the model learns to regularize. Here the model learns to regularize. Like, if you look at this guy with glasses, there are no glasses here. And the reason why is because there aren't that many people with glasses in the training set, so it thinks that particular dimension is just noise. So it removes the glasses. It also tends to remove mustaches, right? If you look at this guy, there's no mustache. It's like kind of like there is no mustache, no glasses. So it basically thinks that that's not an important property for preserving information about the face. So it sort of does that. You can also do the exact same thing, modeling word counts or modeling count data. So this was done with Reuters corpus, where you have about 800 news stories. And what you do is you have a bag of word representation, which basically says which words occur in each particular document. And then you, based on 2,000 most frequent words, you do the reconstruction. You do sort of projected two-dimensional space. From two-dimensional space, you try to do reconstructing back the original word counts. And so this is a PCA solution. Something is called latent semantic analysis, right, of projecting into two-dimensional space. And this is a deep autoencoder. There are no labels. You don't have any label structure. You just have word counts. And you're basically trying to say, how do I find the two-dimensional space such that I preserve as much as possible about word counts, right? So it finds this very interesting structure. Kind of finds that European Community Monetary Economic, monetary economic stuff is next to disasters and accidents, which is kind of funny. That was done back in '97, I think. The data was collected then. You can also look at retrieval results, right? You can say, how can I find similar documents or similar news stories? So typically, if you think about these autoencoders, the way you can think about them is that you have some high-dimensional data, you project in some continuous real-valued space, low-dimensional space, such that you can do very fast nearest neighbor search. So you can find similar items. I think that when I was back in Toronto, one of the students actually built this particular model for WikiLeaks, which is kind of funny. You take a WikiLeaks paper about leaked something, and you go to the two-dimensional space and it shows these are the articles that kind of closest to you. So you can click on it and look at similar articles about Wikipage and WikiLeaks and stuff like that, which is pretty interesting. There is another thing that you can do. You can basically do the following. Because we are using nonlinearities, in principle, you can stitch the hidden, your bottleneck layer could be a binary layer, right? You just stick sigmoids. There are a few tricks you need to do. But at the same time, what you can do is you can map your data into binary space. And there's something interesting about binary space. In binary space, you can actually treat the binary space as a memory address space, right? So you can basically say, if I have billions of documents, I don't need to do nearest neighbor search. I can just look at the nearby memory addresses that are different by 1, for example, right? And find the closest one. So you can look at the Hamming ball of size 1. You can arrange it in the memory in such a way that you don't actually need to do search. It's kind of like, so it's kind of, you can try to retrieve similar documents without doing any search at all. And the 20-dimensional subspace is actually, or the 20-dimensional binary space is actually a pretty large space, right? It's 2 to the 20 possible locations, which takes about 4 gigabytes of data. So you can, if you're able to store it, then you can do fairly good retrieval. And there were like a whole bunch of papers that basically explored this idea of taking input images, embedding them into the binary space, and you can like see, for this particular image, these are nearby images. For this particular image, these are nearby images, and you can really retrieve images very quickly by sort of using these ideas. Here's another thing. What you can do is, just to show you the ideas behind learning the similarity metrics, is what you can do is you can say, well, if I have 2 inputs, right, in this case, 2 images, can I pass them through the same network? Or obviously, these 2 networks have the same parameters. But can I also pass them through the same network in such a way that I map these 2 images to the same point? Right? I want to learn the transformation that transform both of these digits. And I look at the distance between the outputs. And I want the distance between the outputs to be small. Right? For things that are dissimilar, I want them to be large. For things that are similar, I want them to be small. Right? And this is what the model can do. It can actually map these digits into the 2-dimensional space that preserves the class structure, which is pretty interesting. If you look at like linear discriminant analysis, if you look at PCA, it's very difficult to preserve this structure. And this is very useful because in many cases you can't have access to, you just need access to pairs of similar images. You say these 2 mean the same thing, these 2 mean the same thing. And you're just basically trying to map them to the same point in the hidden space. There's a lot of work built upon these kinds of ideas. Embedding different objects into this low-dimensional space such a way that similar objects mapped close to each other. And obviously, if you've seen some papers on caption generation, retrieval, all that stuff is like embedding. You can embed sentences. Later, we'll see in this course. You can embed short clips of videos. You can embed images. You can embed phrases. Everything into this latent space. In principle, I can show you like a video, and I can show you a caption or a text and say, well, embed both these things into the space such that they're close to each other, because they mean the same thing, right? And so that's quite useful. Here's what you can do. By learning the similarity metric, what the model is able to learn, which is kind of interesting, is that some features are learning to learn class-sensitive representations, and some features are actually learning to learn they're learning something about the shape or the thickness or class-insensitive features. So, for example, if I take hidden unit 25 and I start changing hidden unit 25, it changes 3 into 5. which is kind of interesting, right? Just by changing the hidden unit, I can reconstruct it back and decode it and look at what it does. If I change the hidden unit 42, it basically changes the thickness of the ink, right? Like this is a thick 3 and this is skinny 3. So it can capture these different variations in the data. There's some class sensitive, there's some class insensitive, which is kind of interesting. And just the last part, there's been also some interesting work on learning invariant features of tumor signatures, right? So this is more in the health domain. So these are some examples of tumor region and some mixed and such. And here is one particular formulation that I just wanted to show you, which is, let me just see, which is kind of, it's almost like a sparse coding model. We'll later look at the sparse coding model, but it has this interesting structure, right? It's basically saying the way that I'm modeling particular inputs is I have this term, whatever is coming into the hidden unit, squared. This is squared. So this is an encoder squared. And then I have this kind of particular nonlinearity square root of something. So you take the output, you look at the squared. So let's look at what it's actually trying to do. Given a training set, you minimize this objective function. So you're basically saying this is the reconstruction term, and I also want this probability to be, or this particular probability to be small. And maybe, oh, sorry. The reason why I wanted to show you this particular paper is if you look at this particular paper, it relates to independence component analysis, independent subspace analysis, something again we cover later in the class. But the interesting thing here is that by constructing, obviously if you look back here, there is a reconstruction error, right? And you're just trying to reconstruct the original data, but then there is another penalty term, almost like a regularizer, that basically says look at the squares and make sure that the squares terms are small enough as a regularizer. And the interesting thing for this paper is that they've actually shown that this particular model can learn a lot of interesting features. And if you take these features and you apply it, in this case I believe they looked at classification of tumor regions, you can do much better compared to just doing manual tuning, which is what people were doing before. You construct some features, you build some kind of logistic regression. So here it was done in an unsupervised way, right? Because it's an autoencoder. For the domains of medical imaging, there's typically not enough labeled examples. That's a big struggle. So this is where autoencoder style models can help a lot. Okay. So let's finish for today and then come back on Monday. Also, the office hours for TAs for your second homework assignments have been posted. Make sure you talk to the TAs and make sure you start working on your homework assignment sooner rather than later. Based on your first homework assignment, try to manage your time properly.